right, so now I'm going to do a shear stress example. And this example comes with some really fun statics. So that's good. So we have this beam in figure 1.32, and it is supported by a pin at C on the right and by a short link AB. So we're going to treat this AB as a two-force member. The distributed load is 30 kilonewtons per meter. And we are supposed to find the average shear stress in the pins at A and at C. And each pin has a diameter, so given the diameter of the pin equals 25 millimeters. And L equals 1.8 meters. And theta, the angle of bar AB, is 35 degrees. And we're supposed to find the shear stress, so that's tau in the pin at A and tau in the pin at C. And as you can see, they gave us pictures of these pins so we can decide if they're single or double shear. We'll do that later. So to start with, this is a stress, so that means it's a force over an area. It's a shear stress, so we're going to call that stress a shear force. So our guiding equation for this problem is tau, the shear stress, equals the shear force all over the area over which it acts. In this case, that's going to be the area of the cross-section of that bolt. So B over A. All right, but to get started, we get to do one of my favorite things. We have to do some equilibrium of this beam. So we start with free body diagram. And the way I like to draw free body diagrams, especially when I have a two-force member on them, is to just draw the beam, then draw that bar 1 at its angle, so that's F1. And then I'll put in the angle that it's at here, 35 degrees. And then at C, we have a pin, so we have a reaction in the Y direction, CY, and we have a reaction in the X direction, CX. Okay, and then we have this distributed load, which we can draw on here. And that is 30 kilonewtons per meter for a total of 1.8 meters. So I'm going to turn that distributed load into a point load to calculate my reactions. So that'll be in the middle of the 1.8 meters. So that'll be at 0.9 meters. And that's going to be 30 kilonewtons per meter times 1.8 meters. And now we just want a force, so it'll be 54 kilonewtons. Okay, so then we do equilibrium to find the reactions so that we can get the force on these bolts. So equilibrium. So we're going to have to do all three equations because we need F1, Cx, and Cy. So I'm going to start with taking a moment about C. Some of the moments about C, that way I can find out what F1 is. Some of the moments about C equals 0. I'm going to start with this, the distributed load I've turned into a point load. It's going to create a positive moment around C, and that is going to be 54 kilonewtons times half the distance of 1.8 meters, which is 0.9 meters. And then I'm going to use the y component of F1 because the x component runs along C. So the y component of F1, which will be, and that will create a negative moment. So I have minus F1. To get the y component, I'm going to use the sine of 35 degrees. Then I have to take the distance, multiply the distance from C, and that's the full 1.8 meters. All right, and then I solve for F1, and I get 47.07 kilonewtons. All right, now I can either do some of the forces in the x or some of the forces in the y. Start with some of the forces in the x. Here, this all equals 0. This equals Cx. I have it drawn positive. Y and x. Cx minus the x component of F1, which is F1 times the cosine of 35 degrees. And I know that F1 is 47.07, so that leaves me with a Cx equal to 38.56 kilonewtons. Okay, and then I need to find Cy. So I could do some of the moments about B, or I could do some of the forces in the Y. I'm going to do, for some reason, I did some of the moments about B. That's kind of a fun way to do it, I guess. That's what I'll do. Or you could just do some of the forces in the Y. So that would equal, we have F1 times the sine of 35 degrees, the y component of F1, minus the distributed load turned into a point load, 54 kilonewtons, plus Cy. And we get that Cy equals 27 kilonewtons. So the last thing we need to do before we move on to calculating the stress is we have a Cx and we have a Cy. And we have to calculate the shear force acting to calculate the shear stress. So we need to find the resultant force at C. So like we did in homework 1, we're going to find the resultant force at C. And to do that, we just take C, this is like the magnitude of the force, equals the square root of cx squared plus cy squared. So that equals 38.56 kilonewtons squared plus 27 kilonewtons squared. Take the square root of all of that, and we get C equals, and this won't be surprising, it'll make sense once I write it out, 47.07 kilonewtons, which C is the same as F1, which makes sense when you have an equally distributed load here. The force on the left is going to be equal to the total force on the right. So that's kind of fun to see. Okay, so then we're going to need the area of the pin to calculate the shear stress. And then after we calculate the area of the pin, we're going to look at our pictures and determine, will we be using that area twice because it's in double shear or once because it's in single shear? Okay, so the area of the pin we're going to use that area of a circle with the diameter. So a pin equals pi over 4 times the diameter of the pin squared. So that equals pi over 4 times 25 millimeters squared. And we get an area of the pin equal to 490.87 millimeters squared. Okay, so now we'll start with pin A. And pin A is in single shear. So what would happen if we broke this off? It would break right there. We only have one shear plane. So I think if you blow that up, we just have this shear plane here. So one shear plane. So pin A is in single shear. So we will just use the area of the pin once, and we will get that the shear stress of pin A equals the shear force at A, which is just F1. So this force coming out at A is the same as this force coming out at B. So we have F1 equals F1 over the area of the pin, and that equals 47.07 kilonewtons all over 490.87 millimeters squared. I'm going to change these kilonewtons into newtons so that I have megapascals. So times 1,000 newtons per millimeter squared. And I get the shear stress in pin A equals 95.9 megapascals. Okay, so now when we look at pin C, this pin is in double shear. So if we look at this, it has a shear plane here and a shear plane here. So we're in double shear. So that means we'll have to multiply the area of the bolt by 2. So we're going to end up with the shear stress half of pin A, but we'll do the calculation. So the shear stress at pin C equals that resultant force of C all over 2 times the area of the pin. So that equals 47,070 newtons all over 2 times 490.87 millimeters squared. And we get the shear stress of pin C equals 47.9 megapascals. All right, so there is a good shear stress example.